So so all of them under high pressures, high temperatures, the double bonds between them are going to break up. So I'm going to remove the double bonds. And when I do that, the carbon atoms, they've got to be, they're not making 4 bonds anymore. So they're going to, so the 4th bond would be made between them, and they would all start linking up. And that is what is going to be your polymer. It's a large macromolecule that's going to be formed when all these monomers, they join up. Is that clear?
Yes, sir.
And this would be called polyethylene. So thousands of monomers are going to link up. So this one is easy, and the next one, what we're going to do is we're going to make a slightly more complicated. We're going to make a slightly more complicated one. Just hold on 1 second. So we're going to do a slightly more complicated one, which is let's try making a polymer out of this alkene. It's got to be an alkene. So let's say I've got this molecule. There is hydrogen, 3 hydrogens with this one. There would be 3 hydrogens with this one. There's going to be 3 hydrogens with this one. So if you look at this molecule, the very first basic thing that needs to be done is the molecule needs to be redrawn. Because remember, what is joining up? It's the double bonds that are reacting with each other. It's the double bonds that are getting added with each other. So the very first basic thing that you got to do is you have to redraw this. And the way you're going to redraw this is make sure you don't draw anything on the right or the left side of the double bond. If there is anything on the right or left side, make sure you either bend it. You're not going to change the molecule. All you have to do is make sure there's nothing on the right side or the left side. I mean, either turn it upwards or turn it downwards. So here's my double bond in the middle. There's an H that's already in the middle, and there's a CH3 that's on the top side. So where would this thing be drawn? I'm going to just turn it upwards. Instead of drawing on the right side, what I'm going to do is I'm going to move it upwards. So the bonds are not changing. The position is the same. The only the direction I'm changing the direction. Same with this CH3 over here as well. What I'm going to do is I'm going to bend this CH3 downwards. And that's where I'm going to keep the CH3. So is that clear?
Yes.
So don't draw anything on the right or left side. And we're going to draw repeat units now. We're going to draw many repeat units. So this thing would repeat over and over again. So that's 1. That's another one. Let's make 4 of them. And here's another one. Let me just get rid of. The double bonds are now going to go away. You just hold on 1 second. The double bonds are going to go away. Just 1 second. Let me restart this. Yes, this is the one. So let me just get rid of this. It's the double bonds that are going to link up. So the double bonds would go away. They would turn into single bonds. And these groups, the carbon atoms, would start linking up with each other. And that's going to be your polymer. Is that clear?
Yes, teacher. Sir.
Yes.
Yeah.
Ajay, so make sure you know this, how to make a polymer out of a more complicated alkene. Just don't put anything on the right side or the left side of the double bond. We can just do one more example. Maybe let's say I have a propene molecule. So
Sir, so create a polymer, just add how many carbons you want on the left side.
which one?
Like to create a polymer, you can add as many carbons as you want on the left side.
Yeah, I didn't get what left side. The only thing I said was that the minimum requirement is that you need an alkene. So I took a random alkene. Now to make the polymer, these alkenes would join up. So what I said was that I'm going to do another example. That if I want to make a polymer out of butene, so this one has 3 H's, this one has 1 H, this one has 1 H, and this one has 3 H's. So under high pressures and high temperatures, lots of butene molecules are going to link up, they're going to join up. But the first thing that you have to do is, like if you want to draw the polymer, the first thing is don't draw anything on the left or the right side, because it's very hard to actually, how do I link up the double bonds? Because like if I make 2 butene molecules, here's the problem. Like if I keep 2 butene molecules, how can I connect the double bonds? There are CH3 groups that are coming in the way. Is that point clear?
Yes, sir.
So instead, what I'm going to do is I would redraw this. I'm going to just make the CH3 point upward, make this CH3 point upwards as well. So there's going to be a double bond in the middle. The H's would still be at the bottom. And the CH3s would be pointing upwards. This CH3 would also be pointing upwards. It's the exact same molecule. It's the exact same molecule. That's the double bond in the middle. And this is how I'm going to draw this. And I'm going to draw some repeat units of the same monomer. Let's just draw 3 of them now. So here's another one. The double bonds are going to react, and they will link up. Just a second. So the double bonds are going to react, and they would link up. So this double bond is gone, this is gone, this is gone, and they would start linking up with each other. Is that clear?
All right, sir. Yes.
So that's the basic requirement. And the other thing now is that these are your polymers. Think of polymers as so you'll be asked to draw any number of polymers. Another way to represent polymers is that you just write one repeat unit and you write N next to it. For example, over here the repeat unit is this thing. So you just draw one of these and you write N. Make sure you draw the continuation bonds, which are the bonds on both sides. Same is the case over here. You can just draw this part and you can write N over here. N is the number of times it's going to repeat. So this thing would repeat thousands of times. Now, to think about polymers, one thing that you should know is you should be able to predict what the properties of the polymers are. So properties of polymers. Now polymers, think of polymers as these strands. Like your clothes are made out of polymers. So they're these tiny, I mean, your hair is a polymer. So it's these strands that are microscopic. They're not even microscopic. They're at the nanoscale level. And there are lots of them, really long strands. And these strands are entangled with each other. Just like a thread is basically a bunch of like lots of polymers all entangled with each other. Is the idea clear?
Yes.
And
Yes, sir.
that's what plastics are. Plastics, etc., fabric, clothes, all of these are polymers around you. So plastics, fabric, etc. Your anything synthetic is pretty much a polymer. Now I'm going to talk about the properties. The properties are that addition polymers tend to be non-biodegradable. So addition polymers are non-biodegradable, and there's a reason for that. The reason for that is that they are very unreactive because the carbon chain is non-polar. As the carbon chain is
Non-polar.
non-polar, doesn't really attract anything. A carbon-carbon bond is, and a carbon-carbon bond is very stable as well. So most organic chemistry reactions, nothing is happening to the carbon-carbon bond. Cracking requires a high temperature for it to break down. So all these bonds, the carbon-carbon bonds, are like really non-polar. So plastics or polymers that are made out of addition polymers, they tend to be very non-biodegradable. Like shopping bags, they are very non-biodegradable. They're going to last for a long time because they're very unreactive. There are other types of plastics as well. Sorry, other types of polymers. We are a polymer. Proteins are polymers. Fats are polymers. They tend to be very biodegradable. They break down very easily. Even your clothes, your fabric, polyesters, etc. They tend to be very biodegradable because they're not addition polymers. They're a different polymer, which you're going to study in A2. But at the moment, we're just going to study addition polymers. Just remember why they're non-biodegradable. Other things are that polymer properties can be changed by side chains and groups. So they can be changed by side chains and groups. What that means is that if I have a polymer, let's say I want to make a polymer out of this molecule. And the molecule has an OH group as well. So if I want to make a polymer out of it, this would start repeating. The double bond between them would break. And this thing would repeat over and over again. So you can just write N and show the continuation bonds. Now, if I introduce an OH group, a lot of things would change. Like what does an OH group do? Can anyone tell me how would the properties change if there's an OH group in the polymer? Will it attract water molecules? I mean, imagine this as a chain, and these are these OH groups that are coming out of it. So will it attract water molecules or not?
Yes,
It will.
It will.
It will. It will.
Achha, so OH groups, they attract water. So that means it's going to be water absorbent. So I can change the property of the polymer. I mean, your sponges, your like dishwashing sponges, etc. They're very water absorbent, and that's the reason, because maybe the side chain contains a lot of OH groups, and that's how you can change the properties. So I'm going to discuss a few of them, the common examples. One of them is PVC. Now, the reason they're very unreactive is, we already discussed the reasons, but that is a very good property. Like, why do you make plastic bottles? Because to keep water, because it's cheap. That's the first thing. Plus, you know that nothing would happen to the bottle. It's kind of very durable. It's very non-biodegradable. So that's like a property, but in the long run, it's also harmful as well. So PVC, lots of stuff, construction material that's you make PVC pipes. Most of the water pipes in your homes are made from PVC. 10, 20 years ago, they were made from metal. They were made from steel. No, that's no longer the case. So most of it is made from PVC. It's usually a green colored substance. Windows are now made from windows and doors. They've actually recently stopped making windows and doors out of wood, even out of aluminium as well, because both of these are kind of non-durable. So they've started making windows and doors. Wooden tiles are now, or tiles that look like wood, they're actually made from PVC now. So it's basically a type of plastic. It's very durable. Now, a PVC molecule is made from chloroethene, which is that's like an ethene molecule, but with one Cl. So when it polymerizes,
Sir,
yes.
what's the fourth thing you've written?
Which one?
What's the fourth thing you wrote in
Tiles.
PVC?
That's tiles.
Oh, okay.
I mean, you can just Google. I mean, your board. Are you sure your boards are working? Like those links?
So give me 1 second. I'll check.
I am not sure why my boards have stopped working.
So maybe open it like directly from a link, like.
I'll try doing something. I mean, all the notes are stuck there. I say anyway. So this
Yes,
is.
sir. My board is working. The organic one.
That's yeah. Mine is still stuck. It's my internet is fine. I don't know what's wrong. So let's continue. So all these doors, I mean, you must have seen these tiles, etc. These are all just giving you an idea that there are lots of these doors, tiles, etc. They're now made from PVC. They've stopped using wood. They've stopped using aluminium. They've stopped using steel. So this is what PVC is. PVC has if you polymerize it, it's got a Cl. How would the Cl change the property? Like what type of, imagine strands of PVC entangled with each other and they've got a Cl somewhere. So there are lots of strands. So can anyone guess what type of intermolecular force would be present in PVC strands?
Dipole forces.
So there's going to be permanent dipoles, because the CCl bond would be slightly polar, right? So there's going to be negative charge. The carbon over here would have a slight, and there would be a strong attractive force. So there's going to be permanent dipole. So there's going to be a permanent dipole. Cl is electronegative. So there's going to be permanent dipole interaction. And because of that permanent dipole interaction, there's going to be, which is why it's going to be stronger. So more attraction. And that would result in a slightly stronger, more durable plastic. Now this looks exactly like ethene. The problem with ethene was, if you make a polymer out of ethene, what will happen is that it's completely non-polar. So if you have a strand that's polyethylene, there's another strand, they're not going to attract each other very strongly. They would only have very weak van der Waals forces and nothing else. Which is why plastic bags tend to be very soft. I mean, you can pull a strand. Like if I stretch it, what happens? One of the strand gets pulled out of it. I mean, the strands, they kind of slide past each other. So which is why your normal shopping bags, etc., they're very stretchable because they have weak van der Waals forces. PVC, like if you have a PVC tile, you can't do that because the particles the strands are attracting each other very strongly. Is that clear?
Yes, sir.
Yes, sir.
So moving on, so that's about it. That's about addition polymers. The next thing is about oxidation of alkenes. So it's about oxidation of alkenes. What's going to happen in oxidation of alkenes is that there are two types of oxidation. And when we talk about oxidation reaction, there are many reactions that are considered oxidation. But when it comes to organic chemistry, we basically talk about oxidation in terms of addition of oxygen or loss of hydrogen. Or loss of H. So we think of it in that way. We think of oxidation in that way. Because a lot of reactions can be oxidation, but specifically, we're very specific, addition of oxygen. Now, when you talk about alkenes, there are a couple of reactions. One of them is mild oxidation. What mild oxidation is, that in mild oxidation, you got an alkene. Let's say any alkene, there's a double bond. And there are H atoms, and there's a, and I'm going to oxidize it with an oxidizing agent, but it's mild oxidation. Mild means the conditions are going to be sort of mild, not very strong. So there's going to be cold, dilute, and sometimes alkaline KMNO4. So those are the conditions for mild oxidation. And the reaction that will happen in mild oxidation is that this alkene, remember the reaction is with the double bond. So this alkene over here, pretty much everything remains the same except for the double bond. The double bond so the double bond turns into, one second. So in this case, the double bond, it goes away, and instead 2 OH groups get added to it on both the carbon atoms. So again, the reaction is with the double bond. It's like an addition reaction, and diols are formed. These are known as diols. OH groups get added to both the carbon atoms. Is that clear?
Yes, sir.
Yes, sir.
So that's basically a diol. And then you have another type of, I'll just do another example. Let's say I have a slightly more complicated alkene, and I'm going to do the skeletal formula. So let's say there's this molecule. And here's a molecule of an alkene. What will happen if I do mild oxidation? The molecule, so the molecule over here, everything would happen to these carbon atoms, which are on the double bond. So the double bond would go away. This double bond would also go away, and OH groups will get added to both of them. So there's going to be an OH group added. So that forms a diol. This one would also form a diol. And that's your reaction. Is that clear?
Yes,
Yes,
sir.
sir.
So now the second type of reaction is slightly more complicated. The second type of reaction is, and that's again an oxidation reaction. As this one is easy. Wherever you see the double bond, just put these OH groups there. That's it. You add one OH, and there's going to be the other OH on the other carbon atom. That's it. So you add the OH groups. The second type is strong oxidation. So when you do strong oxidation is done using hot concentrated acidified KMnO4. Concentrated acidified KMnO4. Now, when it comes to strong oxidation, what happens is the first thing that happens is that the double bond, wherever the double bond is, it's going to break into two pieces completely. So this double bond is going to split and it will break. Whenever in the molecule you've got a double bond, so the molecule breaks down into smaller pieces because the double bond is completely broken. And you'll have three scenarios. So the fragment, what that fragment gets oxidized to depends on that scenario. So once the double bond breaks and the carbon that was making the double bond had two hydrogens with it, that thing will get oxidized to a carbon dioxide and a water molecule. So that's the oxidation of in that particular scenario. Is that clear?
Yes, sir.
The second scenario number 2 is you got a double bond and there is one carbon chain and there's one H. Now, if there's one carbon chain on one side, then that particular carbon, and remember, focus on that particular carbon. That particular carbon would turn into carboxylic acid. And it will turn into an aldehyde first and then a carboxylic acid, but the aldehyde part is not that important. So it turns into a carboxylic acid. Scenario number 3 is that when the double bond breaks and the carbon that broke off had carbon chains or has carbon chains on both sides, that particular one would turn into a ketone. I mean, it will turn into a carbonyl group. It will turn into acetyl bond O. So it's going to turn into a ketone group. So you've got these three scenarios once the double bond breaks. Now it's you need to practice this. So we're going to do some practice about these questions. So let's say I have a molecule, and the question is slightly more complicated when it's a skeletal formula. So let's say I have a molecule, and the molecule has a double bond in this way. Now imagine. Now remember, in the skeletal formula, they don't show you the hydrogen atom. So you've got one carbon over here, one carbon over here. This thing would split in the middle. The double bond would completely break. So let's do that. And this double bond is going to completely break in the middle. So I'm going to break the double bond in the middle. So that double bond is completely gone. Forget the rest of the molecule. Only the double bond has broken. And you're going to focus on each carbon atom. So can you tell me this carbon atom? Is this carbon atom that was making the double bond? You can remember the scenarios over here are for those carbon atoms that were previously making double bonds. So this one, the blue dot over here, this is bonded to two carbon chains. So if it's bonded to two carbon chains, what should it get converted to? It should get converted to a ketone. So this one over here should be converted to a ketone. And then you have this carbon atom. This carbon atom had no carbon chains attached to it. So if it's got no carbon chain attached to it, it should get converted into a carbon dioxide and a water molecule. So it should get converted to a carbon dioxide and a water molecule. Actually, before doing this, I should have drawn, instead of jumping to the skeletal formula, I should have gone with the with the fully displayed one. Let me do the same thing with a fully displayed one first. So let's try and do this one first. First thing, the double bond would break in the middle. And your focus is on these two carbon atoms. So the molecule would split up. And the entire focus should be on nothing should happen to the rest of the molecule. Break the molecule from the middle. They've broken into two pieces, right? So the first one over here, this one is bonded to one carbon chain and it's got one H. So if it's just bonded to one carbon chain, this carbon atom should turn into a carboxylic acid. It's this one, it's scenario number 2. Is this thing clear?
Yes, sir.
Yeah.
Yes.
So this one over here has one carbon chain, so it should get converted into a carboxylic acid. So just turn that into a carboxylic acid. What's a carboxylic acid? It's going to be double bond ON, OH. What about this one? This other carbon atom that was making the double bond, it is now bonded to two carbon chains. If it's bonded to two carbon chains, it should get converted into a ketone. It should just turn into a double bond and O. Is that clear?
Yes.
Yes, sir.
Yeah.
So now we're going to practice more on skeletal formulas now. So let's start with let's talk about this one. Here's a molecule. The focus should be on these two carbon atoms. The double bond in the middle, if you do strong oxidation, the double bond in the middle would break up and the molecule would split into, it will split into two parts. So this is what you're going to do. The double bond would break and the molecule has split into two parts. Now your focus is on the red ones, the ones that were making the double bond. So this one, it's bonded to two carbon chains, this one. There's a carbon chain here, there's a carbon chain on the other side. So that means if it's bonded to two carbon chains, it should turn into double bond O. It should turn into a ketone. So this one over here should turn into a ketone. And this other one is also bonded to two carbon chains, so it should also turn into a ketone. Is this clear?
Yes, sir. Yeah.
So now let's do another one. Let's say this one. Now this one has two double bonds, so this will break and this one will also break. So our focus is on these four carbon atoms. What will happen to them when they break? What are the scenarios? What kind of products would they form? So first thing, you break the double bonds. This double bond is gone, this double bond is also gone. So I'm going to do that. This is gone, this is gone. The molecule has split into two kind of identical parts. So this one, first thing, this one over here has one carbon chain. Like there's only one carbon chain. So go back. So after breaking the double bond, if the carbon atom has one carbon chain, it should turn into that carbon atom should turn into a carboxylic acid. Is that clear? And again, I'm going to just revise quickly. If the carbon has no carbon chains attached to it, once the double bond broke, that's carbon dioxide and H2. If the carbon that broke away from the double bond and it has one carbon chain, it should turn into a carboxylic acid. If it's got two carbon chains, it should turn into a serial bond O. It should turn into a ketone. So this one over here has one carbon chain. So this one should turn into a carboxylic acid. So it should become double bond O and OH. Is that clear? This one should do exactly the same. Acha, what about this one? It's got two carbon chains, one on this side, one on this side. So what should this get converted into?
A ketone.
Ketone, yeah.
Okay, so that will be a ketone, and this one is, so basically both sides were exactly the same. So you're going to get two separate molecules. In this case, both of them are the same. Let's try and do another one. So let's try and do this one. Now, this is going to break over here. And once this happens, the double bond between them would go away. What will this carbon atom turn into, this one? It's got, how many carbon chains does it have? It doesn't have anything attached to it.
Two hydrogens attached.
So it's got no carbon chain. So which scenario is this? What will it get oxidized to?
Alcohol.
Carbon dioxide.
No.
So it's the first one, right?
Yeah. Yeah.
So that's the first one. So this one over here, this carbon atom has nothing attached to it. I mean, no carbon chain, so it will turn into carbon dioxide. And what about the top one? What will happen to that one? It's got two carbon chains attached to it.
Ketone.
So that one is going to be a ketone.
Ketone. Yes.
So you're going to have, so remember this, we'll try and practice more questions about this. Just remember that alkenes have two oxidations. One of them is strong oxidation, where the double bond would completely break. The molecule is split into pieces, and you'll have three separate scenarios. But any change that would happen would only happen to the carbons that were making the double bonds. The rest of the molecule kind of remains exactly the same. It's just the double bond part that changes. And then you have mild oxidation. Mild oxidation is when you have cold dilute KMNO4, wherever there is a double bond, it just turns into a diol. You just put OH groups in its place. The double bond does not break completely. It turns into a single bond and OH groups get added to it. Is that clear?
Yes.
Yes, sir.
Yes, sir.
Let's continue tomorrow then, okay?
Okay, sir.
Okay, sir.
Allah Hafiz.
Okay.
Okay. Love is.